Hello everyone. Today we are going to discuss a very interesting question from the real analysis. I hope that you all are well acquainted with the Riemann integral, Riemann lower sum, upper sum. All these things will be used here. Okay. What is the question is saying? The question is saying that f is a Riemann integrable function. Then this limit should happen. This lemma is sometimes regarded as the Riemann Lebesgue lemma. Riemann Lebesgue lemma means here we are proving this thing for the Riemann integrable function. But if you can prove this for the Lebesgue integrable function, then it is called the Riemann Lebesgue lemma. But so it is a lower version of the Riemann Lebesgue lemma. Okay. Here interesting thing is that f of x sin nx is going to 0. Okay, we will prove these things for every Riemann integrable function. Okay, before going to prove these functions, we need an auxiliary lemma, auxiliary result, and the auxiliary result is this lemma. Okay, this lemma. What this lemma is saying? This lemma is saying that if we have a Riemann integrable function f, then for every epsilon greater than 0, we can find a simple function. Simple functions are nothing but the step functions, and the definition of the simple function is that the function whose range set is finite one, and the simple functions can be written in this way: summation ai characteristic function of ai, means on these sets ai it takes the value fixed real number ai, means if you plot the graph of the simple functions, then these are nothing but the step functions, means on this set may be a1, okay, and this set may be a2, okay, this height may be 1, this height may be 2, means on the set a1 it takes value 1, on the set a2 it takes value only 2, on the set a3 it takes value 3. So the simple function looks in this way. Okay, and this lemma is saying what? Every Riemann integrable function can be approximated by some simple functions. This is nothing but the approximation of Riemann integrable function by the simple function. And one thing is that that simple function is always less than equal to f. These two things we can find for every epsilon. One type of it is saying that every Riemann integrable functions can be approximated by the simple function. Okay, and this result is obvious because if you consider the Riemann lower sum, the function generated from the lower sum is always less than equal to f, and this is nothing but the LFP for every epsilon. We can find a partition, then we can prove this, and this is the proof by using the Riemann lower sum. Okay, given that f is Riemann integrable functions, so we are looking for f is Riemann integrable function. It implies that for every epsilon greater than 0, we can find a partition p on AB such that this happens, because the lower sum approaches to the integral, and for every epsilon we can find a partition. By using this partition, we can construct the function phi. Okay. Then this partition may be like this. It is from x0 to xl, and x0 is equal to a and xl is equal to b. By using this partition, we will generate our function. We will define that function in like that we usually define for the lower sum. Phi x is nothing but the infimum of f of t for all x belongs to xi minus 1 to xi. It is open interval, so we additionally need to define phi of xi is equal to f of xi. From this construction, it is clear that phi is nothing but the lower sum function, and if we integrate it, we will get the value of the lower sum. Okay, and we know that this lower sum, this difference is less than epsilon, so the integral of phi is less than epsilon. And from this definition of f, it is clear that phi is always less than equal to f. Okay, so this proof is very simple. This is nothing but the Riemann lower sum. Okay, the function which we create from the Riemann lower sum. Okay, this lemma will be used to prove our main result. Our main task is prove this limit, that this limit is equal to 0. Okay, and given that f is the Riemann integrable function. So by the previous lemma, for every epsilon greater than 0, we can find a simple function that is nothing but the Riemann lower sum function, the constructed function from the Riemann lower sum. Let us denote it phi epsilon. Okay, and this looks in this way, and ai's are nothing but the xi minus 1 to xi. Okay, and then we know that phi epsilon f less than equal to f, and this difference is less than equal to epsilon. These two things will be used. Okay, now we will calculate this value. Okay, we will simply add and subtract phi epsilon sin x, add and subtract, then we will apply the triangle inequality here, then we will reach to this step. Okay, then in this term we know that if integration of fx dx there is modulus, then the modulus go inside and we will get this. We will apply this property in the first term. Okay, we will apply this property in the first term, but we know that this modulus of this thing is this, because fx is greater than phi epsilon, so this is a non-negative quantity, so modulus has no effect on this, but it has effect on this one. Okay, sin x can be positive, negative, both. Okay, and this term we are not applying here triangle inequality. In the next step we are simply integrating, because it is a simple function phi epsilon. It is the summation from I from 1 to L, and it takes the value small ai. So this integral breaks to xi minus 1 to xi. Okay, now this and the value of this function is less than equal to 1, denominator by 1, so we put the highest value, so it is less than equal to here, and this one it is. And now we will calculate this integration. This integration nothing but the because the integration of sin x is cos x minus cos x, and here modulus sign is there, we are applying the triangle inequality, then modulus sign will then there will be no minus sign, so it gives the value cos n xi minus cos n xi minus 1. Okay, these two things will come, and additionally here n is there multiplied, so 1 by n is coming after the integration. Then this quantity is a bounded quantity, because cos and sin functions are bounded by 1, so if I apply triangle inequality, it can be bounded by 2, so here 2 is coming. Okay, and this quantity we have already shown that the phi approximate to f, and the integration of this quantity is less than equal to epsilon. We have shown it in the previous lemma, so we have reached to this step. Okay, now one can take the limit on the both sides in this inequality, but we cannot directly take the limit because we do not know whether this limit exists or not. So therefore we will apply the limit supremum, because limit supremum always exists. We are taking limit supremum on both sides as n tends to infinity, because this quantity is a finite quantity, it is independent of n, so this quantity goes to 0, this quantity goes to 0, and so this limit supremum inequality comes to this step less than equal to epsilon. But we know we have epsilon is in our hand, and epsilon is arbitrary, so this quantity is equal to nothing but the 0. Since epsilon is arbitrary, so it is nothing but 0. We have proved that limit supreme value is 0, but we know that limit infimum is always lesser than equal to limit supremum. Since the limit supremum is 0 and the quantity is in modulus is with modulus and means it is a non-negative quantity, so limit infimum is also 0. Therefore from a and b we get that limit supremum and limit infimum both are 0, so then the limit of this function exists and it is also equal to 0. Okay, we reach to this step, and this step is nothing but the limit n tends to infinity sin integral of a to b f of x sin n x dx is equal to 0, and this is our required result, which we proved. I hope that you all understood it very well. Thank you very much.